and to see what students to reflect after they finish the university bachelor degree in our school. So there's a lot of feedback that they particularly in steel structure or the other structures subject as well. So they said it's great. We learn a lot from structural stability, structural member design, concrete and connection. Steel member that we learned last couple of lectures. However, they said that if the connection, how to design connection is a little bit missing. Not missing, but when they actually went out to the industry, there's a lot for them to learn. So we're not covering a lot in our curriculum. So that we found that is something that we really need to focus a little bit more. And of course, connection is very important, very crucial part in a component, right, in the structures system. We pay a lot of attention on how to optimize our structures, get the perfect or the best capacity of the structure member, like we did last couple of lectures. However, to design a connection properly and what is the best, or first is the best solution, and second, based on each solution, how we're going to design for the best. So that is different challenging as well. And of course, I share with you right in the first lectures about the cost. So you can imagine one structured buildings, the cost of connection are not cheap. So particularly in Australia, labor cost is so expensive. So the engineer and the manufacturers for the structure system need to calculate very carefully. They have to calculate the timing and the number of bolts and screws they put in the structural system for each building. Because if you save one screw, and you can multiply with how many screws in the whole building, and then you can see how much time and how much money they can save. So that just gives you a bit of the insights about what's going on, particularly in Australian context. So that I found that maybe it's good to give you a full lectures, and tomorrow as well. So tomorrow is all update, what news, and this is going to go to generally about connection. And the other interesting part that I want to share is everyone probably familiar with how to design connection, particularly in hot rolled steel, right? But cold form steel connection in cold form steel a little bit different. Probably some of them are a lot different. Yes, so especially when you deal with the thin section, and you may expect some failure mode that's totally different with hot rolled steel. So to design that, we need a guideline. So fortunately, we got all the detailed guidelines for designing screw connection or other type. So it's based on a lot of work from back in 2 years ago from Professor Hancock with Professor Colin Raja. Now he's a professor in McGill University in Canada. So I come back to a lot of work from their work back to many years ago, and those work was in the standard that you have now for AISI and Australian standard. Okay. Can you help me? It seems like it's not working. So as always, before I started any lectures, so we'll go through a bit of a sequence, just so you expect what we're going to cover today. So first is I will come back a little bit to introduce you in connection, particularly for cold form steel application, and I will cover all the failure mode and some failure mode that you're not seen in hot rolled steel, and all the detailed design rules for bolted, screw, welded connection, according to AS NZZ 4600 for Australian standard. And I will talk a little bit about new design rules for PAPs, and I will talk about PAPs first. And then, and recently we incorporate the new equation for design of PAPs. And I will go thoroughly to a couple of a couple of examples that you can follow, and just introduce a little bit of what we are doing now, our ongoing research project, particularly for PAPs and the other connection. We are conducting a research now. Okay, so cold-form steel, as I introduced to you before, this is one of the very typical application, that's portal frame. And you can see those all the components, this purlin, C section, Z section. This is super Z because we have a bit of stiffener, and you know why we put the stiffener already. So that is what in Australia, super C and super Z. And this is the other is bridging. The raw bridging to provide lateral restraint. We learned about that, right? We put one in here. We're using steel bar or something, but in Australia we're using smaller channel, and then we lock it into the web. That's how it works. And this is how we built our purlin system in Australia. We use normally a Z section. And we overlap that over the support, so to get the moment, hooking moment. That's what we know, to make sure that the beam here is continuous beam. And the way we did in Australia is we bolted one in the flange on the bottom, not on the top, because on the top you're going to put the roof sheeting on. You don't want to, you want something block it. So just put one in here and one in upper web. So that is how we do it in Australia. And you can see because the flange, the top and bottom slightly different, so you can actually stack on each other, overlap it. So it's how it works. And then we bolted straight away to one click with two bolts. And one click here will be welded to the top flange of the girder. So in order to do that, you can see there's a little bit gap here, so we can avoid the localized loading that we know, right? So, but DSM can allow you to design for that one. So if you need to design that, you can actually check it. So bolted connection, it's the bolt that we're using here with the cold-form purlin. And this one, the other example showing you. This is bolted connection to the girder, and this is the overlap, and this is complex section. You can see this with stiffener, and then flange. So there's that section as well. Right. So now the other application is the cold-form steel portal frame. Normally you see in the application where industrial shed or factory. I'm not sure in India, probably dominated by hot rolled steel, right? Yeah. But in Australia now, we use a lot of cold-form steel. We use the build-up section, back to back, and then between that, we use a lot of bolted together. So it's very light. We're using, normally here is 200 millimeter depth or 150. The thickness roughly 1.9 or 2.4. And that's what we use that for the knee connection and APEC connection on the top. And this one particularly showing you the connection between the build-up columns to the foundation underneath here, like U shape or L shape. And we just bolted to that, and we bolted to the ground. Okay.
What is the depth the concrete at? What is the minimum depth?
You mean the foundation? Yeah. In underneath that? I'm not 100% sure. Oh, that's your guideline for that. I'm not 100% to remember, but there's a guideline and how much you need to build embed to the length of the bolt. Yep. So there's guideline on that. Not in here, but in some handbook from ASI, Australian Steel Institute. You can find that. Okay.
Usually we recommend around 6 inches or 150 mm depth inside the concrete.
There's some minimum requirement. Yes, I can't remember the number, but I'm sure.
Most contractors just do not follow that.
Okay.
They only want 75 or less than that.
Yep.
And we find a hard time because the pouring of the concrete is also sometimes not right. The top 10, 20 mm is somewhat a lean concrete and it won't provide the adequate bearing.
Okay.
So we insist on 150. But I am in the coal pumping company in the US where they say that 150 is too much, they go for 100.
Okay.
But what is the practice in Australia? I would like.
Very interesting to have you to share that one, but I'm sure that there's minimum requirement because I can't get the number exactly, so I can't answer you straight away. But in the handbook, Australian Steel Institute got a series of a handbook about how to design oil connection, and then in that, I'm sure that there's some requirement of the bolt embedment in the concrete. Right, so this is the other common application that I showed you before, but now I just focus on the connection. So this is the main frame of the building, high-rise or mid-rise steel frame building. But the secondary beam in here are made out of a cold form steel. And that C-section and bolted to the I section in the web, you can see here. And interesting, they're using the angle to bolt it here and bolt it here. So it's how it works. And you can look up in here and you can see this is the frame and the secondary beam here. And one thing that you can pick up in here is really interesting, is especially for design aspect. You can see because the C-section, normally with I-beam, hot roll, right? So you have I-beam. Okay, so I draw it and you got I-beam in here. Is that right? But when you connect to the column, and so this is beam somehow, so another big one. So in hot roll, you can always easily to cut that one. So what you call is a coping. You cope that one. So in order to fit our beam here, a bigger one in here, right? And then you got a tab and you just bolt it somehow. So what you do here, you actually move that bolting close to the web. So the idea is to reduce the eccentricity, the better. Cold form steel is a little tricky because the section is going out and it's hardly to chop on the top as you can see here. So that's why in here you can see the top one to the flange, you got a bit of distance. And then you have to connect by the angle here, the angle out, the angle clip. So this is challenge as well for us as engineer. You have to check not just this bolt connection, you have to check the stability, the buckling and everything of that as well. So a lot of challenge in here, but just to share with you how it works in the practice. Yes?
I have a couple of questions. Why we are not following coping here? Is it a problem in practicality?
Why
don't we follow coping in cold form steel?
Oh, you can do it. But then I think, firstly, I think the machine needs to be done to program, to cut and that one. So it's actually take more time. It's all related to the cost, I think, at the end of the day.
What is the maximum gap?
Maximum gap in hot roll, as far as I remember, is 20 millimeter, 10 to 20 millimeter.
Cold form steel?
This one a bit far. Yeah. There's no guide for cold form steel now, I think. Yeah. So that's what we look like. It's more than 20 millimeter or something. So you can decide. The gap here just to make sure that it's not, you have enough space to fit it in. Otherwise, if it's just right there, so there's maybe some imperfection or something like that, you can't fit your beam in. So that is the purpose. Right, so very interesting, the problem with us as engineer, you have to calculate that. Yeah.
The reason I ask is that we have done a good number of connection tests. And we find that there is more eccentricity than the clip angle thickness needs to be increased.
Oh, yeah.
And if it is very closer, then the clip angle is more towards shear.
Yep.
If it is a little farther away, then it increases twisting and the clip angle undergoes shear buckling.
Yes, a lot of problem, right? Yeah, so we're trying to get to that situation where we need to just deal with the shear only. But then you can see that panel will be subjected to a lot of shear problem, shear buckling, yielding, and a lot of other complicated problem, and instability as well, right? Easy for it to be unstable. Yeah. So very challenging, but that is typical. That is the nature of cold form steel.
On both sides or only one side?
Only one side.
Only one side.
Yeah.
The clip angle is on only one side.
Yes, only one side. Yes.
What thickness of the clip angle is the same as the number thickness or any minimum requirement we have to?
It's a good question. Depend on. I think normally it's thicker. It's thicker, 3 mil or 4 mil. Yes. So and normally I'm not sure that they use the high strength steel or they're using normal strength steels. If they use normal 300 grade, then it needs to be thicker. Because high strength steel is normally in the coil to make the purlins. But for the other bit, they normally use the normal strength steel.
There is a lot of gap between the main hot steel and the bottom steel.
Yeah, so as Professor Madhavan told, just mentioned that there are a lot of problems with that in the structural enduring problems. So we have to deal with that a lot. So not like in the hot roll here. We can do it, so we can chop that one easily with the laser cut or whatever we use in the factory. You can do it.
There is another question.
Yeah.
Our studies indicate that screw is unreliable, whereas bolts are more reliable.
Yep. Yes.
Most industry people go for screws.
Yeah.
So what is your thought?
I show you why we use a lot of screw. Okay. Bolted. I share with you a little bit data. First, screw is a lot faster. I show you what a couple of applications why they're using screw a lot faster. The second is the screw. With screw, you don't need to pre-drill. You don't need to have the bolt, the pre-drill hole before you bolt it. And because of bolt, you need to pre-drill it. So normally in the standard or in the practice as well, you need to drill the hole bigger than the diameter of the bolt for installation. Otherwise it's hard, right, to fit in. And once you got that one, and of course you got some slack at the beginning. It's not like screw when you zip in and that is stiff. Everything is straight away working from you apply the load. But in the practice, when bolted, smaller than the house, when you apply the load, always there's slip and always there's slack on the stretch. So that's another thing that we need to consider as well. So there's a lot of things for cold form steel. And I think bolted probably too strong for cold form steel. Cold form steel, bolted is for hot roll steel, but for cold form, yes, in some application like this one, bigger section, but for smaller section, screw is more practical. And I'll show you later. So the other, so you see here, the main cold form steel bolted to the columns, and this is secondary one to the primary one. And they're using all one clip on here, and they bolted here, and that's it, and how it works. All right, so this is, I'll show you that this is the truss system in cold form steel. So everyone knows the truss, right? In hot rolls, normally we use the angle or the other type of hot roll section, and then we bolt it. But in here, you can see they're all using cold form section, so channel section, and the bottom we half section, and then what they do, they just screw it together very fast. So this screws connection. All right, so to answer your question here is, with cold form steel, all those truss are already fabricated in the factory, and they can stack on like one stack like this one, because it's so light, so they can carry like 20 of them or something, and they did it in the factory, so the reliability or the accuracy is very good. So then when they bring it up to the side, you can see two guys on top just put on together, and they just zip. No, they just put the screw together. It's so quick and it's so easier for them for installation. Right, so the other one is the reason why they're using a lot of screw connection. I show you in here. You can see that they punch a little bit indent in, so they dimple it a little bit. And the dimple hole, there's two purposes on that. First is maybe they strengthen a little bit of the shear capacity, but importantly for the second reason is they locate your member accurately. So what you do, you got that dimple, you put that together, it zip and exactly go into the one that you want. And if you don't have dimple, you may be slightly off and you don't know exactly where it is, but then they use dimple, and normally they punch a little bit of a smaller hole, so to guide the dimple hole, and then what the workers just come and zoom into exactly where it is. And remember, all bits and pieces in here, they computerize it, so the location and the size are perfectly accurate in the factory. So what they do, just bring to the side, put together, zip it up, and then do it very quickly. So that's how they can install the cold form steel connection. And you can see in here, it's very fast, it's very speedy to do it. Yes? Yes, a good question. There's two types of screw. One is self-tapping, and self-drilling. Okay, so this one, they use dimple holes, and if they make a little bit of pre-hole drill, they use self-drilling screw. But if you have nothing and you want to tap in, so they're using self-tapping. So they have the top bit as the screw, as the drill. So they just zoom in and then they just go easily. Yeah.
What about the other end? You have a screw head here.
Yep.
After you are driving into the number, the other side the screw is projecting out. Is there is
It just leave what it is. Yeah, they're just sticking out like this one. Yeah. Yep. All right, so you can see in here there's screw connection, and they can screw together a bunch of that. So a build-up section, not just one section, there are three sections they just put together to make sure that you have enough capacity. And not just for small component or small structures. You can see it's a bracing of a big structures. So they got a bunch of screw in here as well, just to make sure they have enough capacity to carry all that big load. All right, so this is one example for a bracing system in a mid-rise building for a cold form steel structure.
What are the cross sections? Side section, the bracings?
The bracing in here, I'm not sure 100% inside, but I think this is a strip. This is the plate, yeah. You can see the plate, the strip. You can they screw here as well. They screw in the member as well. So this is just the plate for the stripe, and they just screw it. So that's why they have two, because it's gonna be always in tension. So that how it works. So there are a lot of work on research. If you look at, I think, Colin Roger in McGill doing some pricing. And recently, Professor Liptek from University of Wollongong tested a lot of pricing like this one in Australia. If you're interested in that research area, I can send you some paper. So at the moment, I'm aware that he just tested a whole system for using those, I think last month. Right, that's typical screw connection, and that is a problem I'll tell you before, right? Because of the flange, so they have to have a bit of piston between the end of this beam to the web of the other beam. Yes?
How do you determine the number of screws?
How you determine that? Yeah, so it's coming back to the design problem. You have to work it out what is the load applied to this connection, and you have to check. So I'm going to talk about the design methodology, but with the design of the connection, it's really simple. You just assume that the connection subjected to every single action, okay? So, or subject to different failure mode. For example, you check for that screw for shear, and you check for bearing, you check for tilting, everything that you check, and then at the end you choose the smallest one that will govern your design. So importantly is you got a big load and you divide it by number of screw, and you got one single capacity of one screw. And one screw that you can compare with different failure mode, all right? Tilting, bearing, shear, whatever, and you have to check it. And if the smallest one is that the one you govern your design. And then if your connection need 10 or 20, you just time with number of screw. Do I answer your question? Good?
Do we test the screws in tension and shear?
We test everything. I'll show you later, different failure mode, all right? We test it in shear, in tilting, in bearing, in pull out, in pull overs. There's different failure mode. So we have to make sure we don't miss any failure mode. It might happen in the practice. So the problem here, not the problem, but the idealization now in here is we treat it as a separate failure mode. We not consider that is a little bit of interaction between the failure mode. So that is why we keep it simple in connection design. I'll talk about that design later for all equation. Yeah.
Any idea what is the maximum thickness of the cold form steel up to which screw will be effective?
Very good question. And I did a lot of tests for high strength steel, and I found that 3 millimeter is a little bit tricky. It can go on to, first it's 3 millimeter, but then the second place, if you go another 3 millimeter, it's gonna be burning a lot of, we try and it fell a lot of screw, it doesn't go through. So it's quite challenged, but in practicality, you can use up to 3 millimeter. Yeah.
Our studies indicate up to 2 mm maybe screws are okay.
Yeah.
Beyond 2 mm.
Yes, a little bit. Yeah.
12 mm bolts.
Yep. I got the same that with 3 millimeter. Oh, it's very thick and putting a lot of effort on that. All right. So the other type of connection is welding. Okay, it's weld connection, and probably very popular, very common in hot rolled steel. But then again, you can use that in cold form steel as well. So this is another example showing the bracing system, and this is where they welded into the frame. And the other interesting one is not really common, but this is part of research from Professor Mahendran from QUT from Australia, where the idea is they come up with 3 bits. One is web, one is top flange and bottom flange. They're all separate. So what we're using rivet. Just clip it together. along the length of the member. So this is the rivet. So they clamp that, they screw together top and bottom flange. That's the other idea. However, I'm not sure that is common now in the practicality, but it's not a way that we can use for cold form steel. All right, so that is interesting as well. Showing you the connection between the columns to the bottom chord. Yep, and you can see they have something inside, just to nail it down to the bottom. This is probably the slab to nail it down to the underneath, the below the level. So they got something similar to that. Transfer the load to here, and the load transfer to the web of the columns.
So, Carl,
Yes.
typically in India we use the grinders as hot rolls. Whenever there is heating connected to the ignition.
Yeah. So the company is very Simpson. Yeah. So they came to our lab, and then they sponsor for us a lot of that. But
So what is used in Australia? Hot roll or cold roll?
in Australia, they use cold form, and then you remember Kim test with 2-story with the high shear load. Even their maximum one, it couldn't carry the shear load. Then we have to make it our 10 millimeter thickness of hot roll steel. Yeah. So I think that's designed for low rise with very low lateral load. But when we test, remember we test, I'll show you a bit later, 2-story for shear wall, and with the huge lateral load. Of course, when it's just drawing for you, it's easy. So what we're trying to test is we test the shear wall, that is the floor. So we got a 2 floor, and we're pushing a big load in here. So what happened, you push it there sideways, and it's put in the shear wall. It's gonna be like that. Right, so instead of you got a shear in here, but you're gonna have a big load in here as well, which just lift that one up. Right, so this is very important. If you don't hold that one, then that one just twist, to rotate, that one will gonna go up. So that is one of very important bit in our structural component, not just shear wall itself, but those you need to pay a lot of attention on that. So the one that I talked to you from Australia, we're using, first we cold form steel thick one, but it's not gonna work. When we test that one, it just lift it up, and there's a big gap in here. So it fell in this connection, not fell in the shear wall. So that's why we have to replace by this one by using 10 millimeter hot roll steel. We have to make our own one. And that's just something to share with you, the challenge. Yes? For limited thickness, limited for cold form steel.
For welding.
For welding, there's, as far as I understand, is there no limit? You mean the minimum limited or the? Yeah, I don't. In the standard, doesn't have any minimum. You can weld it to 0.4 or 0.475 millimeter thickness or cold form. Melting.
What type of welding do you use? Is there any special welding that you use so that it doesn't melt?
That is the you talk about the welding technique. That is probably out of my knowledge. So we need to check with the company of or who provide those type of technique, and you need to look at that one. So yes, it's possible. They have different technology to do it, different way. Maybe Professor Madhavan did a lot of testing on welding, so you have some tools in your lab as well. You can share with.
I explain the context because sometimes we get nasty reviews from the reviewers stating that it will melt. But we have done enormous tests that it will not melt.
Okay. Yeah.
So we wanted to know if there is something that you can add to that so that it reinforce our confidence.
Yeah, yeah, that's a good thing. Yeah, I take your point, but I'm not aware of that before. Okay, so we can discuss later. Now, the other one that I share with you is PAPS. I talk a lot about that. But now, have you seen something like that? I'm sure you see that in concrete or in the decking when you nail something on the concrete block or something. So
It's used in wooden structures.
wooden, yes, you do. Yes, you can find a lot of. It's really narrow, very thin and small one, and then you can punch it in the timbers or in a very thin one. But this is the heavy one. So the diameter is 4.5 millimeter, quite thick, and then it's short like this one, and it's very powerful. It can be shot into the 20 millimeter thickness of steel easily. They can go and embed it in that one. So I show you here two type of guns that we tested in Australia. So it's on the left hand side is the one from Hilti. This is European one, and then this one Ramset is American products. And you can see the dimension of those that we use. So diameter is 4.5. The bigger one is 7.4. It's quite big, chunky. And this one a little bit smaller, and this one is 4 millimeter diameter from that gun. So what happened is the way they do it very quickly. You just put everything on in the position, and the technician or the worker just go and punch it. That's that one. It's very quickly and it's very powerful. So I show you next, so you see how it works. So you go around and they punch it. So that is how he connect the top decking to the top of the beam or something in underneath that. But they are steel structure.
Is it hot rod or cold form?
You can go to hot rod or cold form, but interestingly, the PAP is going to, they need the minimum thickness, not maximum. So normally the requirement now, you need to go to the base, minimum 6 millimeter. Otherwise, if it's so thin, it's gonna go through. It's because it's so powerful. When you punch it and then that's it, it's gone. So you need a quite thick and decent thick base to get it. Yeah. Yes?
You said that minimum 3 mm thick, the screw will be good. The bottom side will be good. So if I want to connect a 2-3 mm back to back, then I will twist it. The same thing will go for this power actuated plasma. What about this pull-out capacitor? For filtering screws, we have that.
Yeah. So it's a very good question. So that's what we're doing now. We test a lot of that PAPs under tension, or even under combine. So what we do, we build up interesting rigs so we can rotate and we can test it under different angle as well. So if you put 90 degrees, it's pure shear, but then when you rotate it and then you got something until you got 180 degrees, then it's pure shear, pure tension. So you actually pull it up. In some case, like in the roof system, if you punch it down and then if the roof is subject to the wind upload and it's gonna blow up. Okay, so that is how it works. So you can see in here, you don't need to pre-drill the holes. The energy from the gun, it just drives the PAPs right into the steel plate, and then because of big impact, there's a big plasticity happen in here. So actually a lot complicated in here. It's melting that steel, and remember that that paths, they have knurling. It's not smooth. The surface is knurling. So then when they done this one, they actually bow and biting together. Right, very, very, very tough. So that is the reason why it's a really good connection and then very good application, particularly for steel to steel.
So can we do it for a roof also?
Can we use that for?
Or passing the roof to the panels?
It's possible, yeah, it's possible, but depend on what you like to do. But with the roof, normally you don't need that very powerful things. You need normal screw. That's fine because roof to roof, it's very thin to thin. But this one, we talk about the major connection, like you connect the cold form steel to hot rolled steel maybe. And normally you can see the previous photo that they need 2 bolts. So the reason, the question now, whether we need to replace those 2 bolts by those 2 paps. Because bolted connection, as I talked about, it takes a lot of time, right? You have to pre-drill the plate, you have to pre-drill the cold form steel, you put together and you have to slot your bolted and you need to tighten up. There's a lot of work. But this one, imagine if you just put together and punch it and that's it, gone, done. So that is how it works. And the other beauty of this one, as you can see, similar to screw, when it's in the position, it means that everything is locked. Stiffness, everything's just very stiff. But bolted, you got a bit of looseness, or you got a bit of tolerance. So that is the other one that we can consider, right, in terms of structural engineering design. So this is how it works, this knurling that I talked about. And this one you can see driving in here. So the steel plate is a lot thicker, but it's still going and embedded into here. So this is how it works when it's cut, and then you can see how the paps work. So that's really interesting. The paps company and even the steel industry, they come and talk. The application of paps is in concrete is long time ago. It's not just something they just invented. However, they're very popular for concrete, as I mentioned, or the composite decking. So they're gonna punch out one on top of a concrete block or something to anchor it. So that's what they call it anchor. But for steel to steel, there's less application. So especially in Australia as well. So that guns from steel to steel, we couldn't buy in the Australian market. So they have to ship all the way from Plantenstein, this headquarters in Europe, and they ship to us to test even all the what they call the jar. The jar is the power, and in the nail as well. So on the gun and jar scale, it's like the gun. You can adjust the power. There's some different level of power depending on the thickness you choose, and then it give you more or less power to do it. It's very, very complicated, but it's innovative, and if it works, it's going to be a wonderful connection because you can save a lot of time, and it works very well. It can carry quite big load. Yeah.
Actually, we came to our office for the demonstration of this.
Did you?
So this hot roll steel, hot roll steel.
Hot roll steel, right?
We mostly work in the petrol industry.
Yes, yes.
Later on, some support system comes in a wall.
Yep.
So it's not like you can go with the bolt.
Yeah, yeah.
Our welding is also restricted because of
Yep.
gas situation.
Yes. So imagine another connection as well. If you have, in the practice, if I section is open section, easy, right? You can drill the hole and then put the bolt nut and you can go on the other side, you screw it up. But look at if you have a hollow section, how are you gonna do it? You have to have a ply bolt or the other way. So in here, you just put it on and then punch it, and that's it, it's done. So it's the beauty of paps. Hopefully we can be used a lot later. So,
Screw rotate when you push it.
sorry?
When the gun pushes the
Yep.
screw, does it rotate?
No, it just punch it. Yeah, straight in and stay there. It's a big bang. I hope that I bring it in here to show you, but this is still not very noisy because it's big impact on that. Yep.
When you do so, I can see that some fumes are coming, right? Some heat is generated.
Yes, a lot of, a little bit hot there. Yes.
But it will change the
The property.
property of the material.
Yes, so I expanded here. There's a lot of plastics is happening here. It's melting. So
So it will alter or you can have some resistance.
yes, and then it's changed.
Will it change the
Yeah.
integration?
We trying to go to that research that area where we think we're gonna cut in the middle of that perhaps and trying to test the fracture toughness and test all residual strength and see what's going on with the area, particularly the area close to the paps. What's going on? The property will change and how it changes, how it works. So it's very complicated. Even the microstructures of the steel around that one as well. So that's the ongoing. We're trying to have a couple of master students to look at that. It's an interesting topic, but I will give you an update later. But as you can see here, there's a lot of things that we don't understand yet. So we really want to do more research. But at the moment, at the structure scale, we did a lot of tests on that to understand. Right, so the connection, and then again, in that book, Professor Craig Hancock written, you can find every detail on that. I found it great. So this is the old one. The previous edition is number 4, and this is the number 5 that he just updated. So in 22, and this one in 2007, quite a long time ago. But this one, you can find that in the website of ASI, okay, Australian Steel Institute. So I recommend, if you're really interested and get into cold form steel, you should have the book. Very easy to follow. He cover all from fundamental theory to the applicational design of that. So he kindly allowed me to use all the information that in the book. So all the example later I show you, actually I copy from his book and to explain to you. Right, so in the book here, he will cover, or I will cover later on, all the design of bolted, screw, and welded connection. Right, back into your question. So this is philosophy of the design of connection. So we think about the connection strength is a chain like this one, and each loop of the chain is one failure mode. Or the other word, the other technical word that we call is one limit state. So we pull in the chains, and of course, it's going to be broken. It can broken in either of them. So whatever in here, either of them broken, it means that our connection is broken. So the methodology here is we have to make sure that we check every single failure mode or limit state. And which one is the smallest one that will govern the design. Okay? That's how it works. So back again, the optimization. So you don't want to design a connection where you choose very big bolts. It's carry a lot of work, but then it's fail in bearing. You know, big bolt in a very thin section, then it's just bearing in the thin section, so it's no point. So we have to optimize that in a way to maximum our connection. Right. So this is the methodology, how to design for connection. So with bolted connection, now you can see in cold form steel, we have bolted, of course, and very popular bolted is in Australia we use metrics. M8 is 8 millimeter, M10, M12, and with the bolt property or type of bolt, we have 2 type of bolt. One is 4.6, which is the normal strength bolt. So we're just using for secondary purposes, not for structural purposes. So the strength of the bolt is about 400 megapascal. For structural purposes, we use high strength bolt. It's 8.8 in Australia standard. And with that one, the yield stress go up to 830 megapascal. And recently, in Australia, we are allowed to use in super high strength bolt. You can go up to 1,000 or something megapascal for the bolt. So at the moment, you can go up to more than 1,000 megapascal. All right, just something to share with you. And in cold form steel, normally you have a double shear one, very popular in hot rolled steel. You got one and you got two lap and then just bolt it. But in cold form, you normally see the one in here with single lap shear connection. Right, so just showing you a couple of filer mode that you might interested in here. So the first one is shear filer, where you have quite all right, so what's happened? You see that? What? Yes, shear failure of the bolt. So it's happened when you bolt it between the two very thick plates, and if you're using the normal strength steel, it just go and cut out bolt in that failure mode. So this is a bolt in shear. Okay, so first failure mode that we see. And the next one is the tear out. You can use gradually, and it's just bearing and tear out our plate in here. You can see this one 8.8. I just mentioned is super high strength steel. There's no problem with the shear, and with that one is thin, so that one is just drag it that piece of steel. Yes. This is the tear out, not bearing. Yeah. So a little bit similar between bearing and tear out. Bearing, it means that the distance between the edge to the bolt is a little bit further, and the bearing, it just keep dragging, and the hole is keep deforming. Is the like a slot shape. It just keep going. That's bearing. But with tear out, when you get when you get close to and when you get close to the edge in here, that whole bit will be gone. So it's tear out like we see in here, okay? And with bearing, and if you have bolt in here, it just keep going in like this one. So this is bearing, okay?
So usually the tearing may happen, since it is in the edge, it is punching out. Otherwise it should be perpendicular to the application of forces.
So this is, this is the direction of flow.
Fracture will happen perpendicular to the...
Oh, that is the other, that is, yes.
Since it is at the end, you are having such a...
So that is the other failure mode. It's called next section. So it's even that if you have not long enough, it's not big enough, sorry, and then it's fracture here. It's just pull out. So this is next section. It's the other failure mode. Okay, so you need to check every single failure, make sure that you don't miss any failure mode. All right. So this is failure, and that's the one. Next one. That's what you talk about. It's similar but very thin. So it means that because of big bolt, you don't have enough area to carry. So what happened? You can see. Exactly what you say. All right, so it's cut out right in the weakest section, where this you have to minus with the net area. Yes, question. You mean the curling? Yes, curling is the other problem as well. There's a lot of reason behind that. Eccentricity is one of them. And there's a lot of things happening when it's become unstable and it curl. Yep.
Real life, we are using the staff system because these are just large bricks.
Yes, it can happen in the practice as well. I'll show you what's going on in the practice. But just on that one, I had one of my PhD students, he finished already, so we got two papers on this one, just looking at the curling that happened in both connection. Sorry? Both tilting, that's very good observation. Tilting is normally happen with screw. I'll show you later on. Yeah? Normally with bolt, we're not looking at tilting. Right? In the standard, you don't have tilting for bolt. Yeah, but screw, yes. I'm going to show you that failure mode later. But with bolt, normally we're just looking at different like this one. Right. Back to your question, right? So normally we have truss, the scope from steel, and you have the other member, which is an co-form channels as well, okay? But to do that one, normally they cut the web like this one, and they screw it in here. Screw to the other flange of the top cord. So in this one, this is the flange lip, right? So in this case, you're gonna have something like this one, right? So lip doesn't not always exist to have in this case. Get it? Good.
The top is lip, right? Only the bottom is not.
The top one?
The top portion of the C channel will have lip.
We don't have lip. Depend on the company. Some company, the Endo frame from Australia, they have plan section, no lip. This one. Yeah. So it's a little bit weak. So we do a couple of tests now and see whether it's a good idea or they need to fold the lip in here. But the lip is very complicated in this case because right in here, the connection, you have to cut the lip to fit that one in. So it's going to be a little bit tricky, right? When you go up here, you have to cut the lip, and then you fit that one in, and then you screw it in here. That's how it works in the practice. All right. So on the detail, it's a little bit more complicated than we thought. But the thing about that, I do it. Right. So you can see here, back in your question, right? This is tear out. The distance between the bolt to the edge is small enough, so they just pull that piece of steel out. And you can see those shear cut in here. That is she planned that cut the bit of steel. This one quite long, so it's just bearing, just dragging the hole, getting elongated, longer, but it's fail. It doesn't pick up the load, so you stop that. Right, and this is the next section that we see. If you use big hole, a smaller strip, then you have that failure mode. Right. So in the standard, we have based on those, we have the equation for different failure mode. So we're gonna have equation for S tail, we have equation for bearing, and we have equation for tension fracture. All right. So this is the calibration where you get all the equation, all the tests in here. Those tests actually was conducted in our school. So just we are very proud of those rules in AS 4600 for screw and bolted connection. So came from our works or from our lab. So this is the equation, tear out. You can see slightly different with hot rolled steel. And so depend on the coefficient in here. And from that, you just look up the table, and then you can find out depending on the thickness that you use. So that is a little bit more about the equation in the standard. And for next section failure, if we use single bolt with washer, and you use this equation. So with that washer, it's different. So remember, washer play an important role in the bolted connection. So in the standards, clearly showing which case you use washer, then you have to use slightly different equation. So very detailed, but it's cover every situation or any scenario in the practice. So this is multiple case. In the previous standard, they just take the net area times with FU. But in the new edition, they have a more complicated, but it's closer to the test. So you can design more accurate more accurately based on the new standard. I will talk about what news in the standard later tomorrow. But today, just give a big picture about what's going on. So the shear failure, the first one, when you just cut through the bolt. So we just copy from the hot roll standard, AS 4100. Just for you, if you're not familiar with Australian standard, 4100 is hot roll steel and 4600 is cold form steel. That's two numbers that you remember. And in here you can see this is only AS. But with cold form steel, we have AS/NZS. So what happened is with steel standard, we have our own one, and New Zealand, they have their own one. So just share with you why we have our own one, because Australia, we're not in the seismic area, earthquake sensitive area. And everyone knows that New Zealand, they're right in the very critical area for earthquake, so they have to have a separate steel structure code. Just they put a lot of the rules and equation related to seismic loading design. So that's why we need to separate. That's to give you a bit of the inside behind that. So shear in here is very simple. This is coefficient, that's the FU, is the ultimate strength of the bolt. And in here is AC and A0. Because of the bolt, you have the one part is shank and one part is threaded. So with threaded, of course, you lose the area. So that's why you take into account that one as well. So depend on your shear plan going to threaded part or shank part, then you can decide what you're using here. All right, so combine action, tension and shear, you're just using that simple interaction curve, and then this is a circular interaction curve, and you can design for that. Block shear rupture. Right, so it's interesting as well. If you have a series of bolts in connection that you can see, and under tension that can, cut that piece of steel out, and that causes the block shear failure mode. We need to check carefully as well. So depending on the situation here, then you have to have different equation to check. So now, just give you an example how to design a shear connection. Okay, so imagine we have two strips of steel. There's two bolted together. And then this is the distance. So df is the diameter of the bolt. Okay. So what we do first is we the diameter of the bolt is 12 millimeter. And in the Australian standard, we need to have at least 1 mil of tolerance. So on each side. So it means that you got one bowl in here and you got one hole in here. So one side here, at least 1 millimeter. That's how the tolerance requirement. So that's why when you calculate the hole, you need to plus 2. So you got two sides. So diameter of the hole is 14 millimeter. Then you calculate the net area. So the area of the cross section of the steel where you deduct the area of the missing holes, right? Because we drill the hole. We calculate that, and then we calculate the tension load with the area, with the section out of the bolt. So this is the AG, is the whole cross section. But then we need to check the area or the section that go through in the middle of the bolt. So that take into account the net area. So you're using that equation. And with this equation, remember we use FU. But this equation, we use Fy. Because with bolt, remember, the stress distribution in the cross section of the bolt is not that simple as we think. So if you have bolt in here and subject to tension, right? So the stress distribution in here somehow is like this one. Right, so we got a lot of stress concentration in here. So for that reason, we got a bit of factor down in here, 0.85, and importantly, we're using FU. It's ultimate work. KT factor is depend on how you put the load together. Yeah. If you have the symmetric one, two nice, KT is 1. And if you have one in eccentricity, you have different KT. So it's all detailed in the standard. Okay, so let's give you an idea about this. But with NT, cross section, that's it, easy. You're using Fy, FU stress. Right, so then we choose a minimum one. So with clause 5533, if we're using the washer, then you calculate the MS based on this equation. Okay? Yes?
What is F and what is the reaction factor? 0.9.
0.9?
Small f.
It's the load factor, isn't it? The load factor. Yeah, 5 factor, 5. You have you design everything and then you time with load factor at the end, 5 factor. Yeah, it's 0.9 in this case. We keep going. Sorry, the 5 factor is down here, 0.55.
So in Indian code, for 0.10 is usually used when the failure is rupture, block shear, or things like that, we multiply by 0.9.
Yep. I think that 0.9 came from. I check with that 0.9, okay? I will get back to you. But the 5 is 0.55 in down here. And you can see now, the load factor for connection, pretty low, isn't it? Yep. Only 55%. So because it's so dependent on a lot of uncertainty, the quality of the bolts, the quality of the holes, and how much the technician experience on how they're going to do the work nicely. And the other uncertainty is what we really don't know is the bolt property as well. We based on the manufacturer catalog or information, but then we don't know exactly. So that's why we need, when we calculate, when we validate, when we calibrate the shear equation, bolted equation, a connection equation, 5 factor is really low, 0.55. So number of bolts required, if we use normal strength bolts, its MPUs is 400 megapascal that I mentioned before, and we can calculate A node is the area of both with the shank one, and then we just put in that shear equation, and then we can calculate the capacity of one bolt in shear.
This one is the bolt core or bolt diameter?
With the bolt connection, bolt in shear, of course you're using diameter of bolt. Because that's looking at the bolt capacity, okay? Right, so you can see if we use, we calculate based on bolt in shear with Talmud tree, the capacity is 67. It's a lot greater than what we calculated before. It's 30.85. Sorry?
In the picture, it is shown as the bolt hole diameter.
Yes, this is when you cut the hole, DF. No, DF is the bolt. DF is the bolt. Yep. So, but the hole is a little bit bigger. DH. Okay. Okay, we should put that one is, this is look like a bolt, not a hole. We bolt in, yep.
It's a bolt.
Yes, the bolt. DF is bolt diameter. It's smaller than DH. DH is hole diameter. Okay. So we've been through this one. So in the case that we don't know what plan going to what, as I explained to you, the bolt can have two parts like shank and then threaded. We just assume the smaller one just to be conservative. Yes? Usually we
Existence will be taken as 1.5 times of diameter of hole.
This one is the dimension that we design for this one. It's just the distance from here to here is 1.5 diameter. Diameter of hole, is it? Okay. I mean, as an engineer, if you're confused about those two, you just choose the worst one, the conservative one to do it. That's on the safety side. You know? If you're not sure, just choose whatever is conservative. All right. But in here, I understand you said that the minimum, right? It's written in there is DF or DH, right? Okay. So whatever is written in the standard, I can't remember. It's DF or DH or DF. The minimum. Bolt diameter? Yeah, so that's DF. Bolt diameter is DF. DH is hole diameter. A little bit confusing with hole and bolt, isn't it? Because it's slightly bigger. So there's a lot of confusing on that as well. Now, bearing capacity. So you have to use that equation. And interesting in here is still using both diameter, not hole. So the reason behind that, because with your bearing, when it's bare, imagine you have a big one like that one, you have a big house, but then you have a smaller one in here. So when it's bearing, it's pushing here, so the fracture is somehow in here, okay? So this is more than DF. Yep. The DH, yes?
Asking we are taking the distance from the center of bolt hole to end of
That I know that is a bit tricky. Yes, yes.
The ends of the fastener to the end of the material.
That's a little bit tricky on that one. Yeah.
The minimum,
You should take in from the center of the bolt, not the hole. Yeah, yeah.
Still is following the center of the bolt.
Yes.
But in saying that they can only fasten the edge from the end of the material.
So I think there's some confusing on that because of the different, the center of the bowl and center of the hole, right? Yeah. So I talked to Professor Hancock already. Yes, he said yes, there's some confusing there. But then as you an engineer, you just choose the worst one to design for that. But in the practice, I understand what you mean is from that is this distance, right? Or that is this distance, isn't it? From here is from the bowl and here from the hole.
Yes, it becomes faster edge of the fastener.
The edge,
Edge of the fastener to the end of
so the edge here,
The circumference.
This one?
Circumference, area of the circumference.
I couldn't get your question, sorry. The top?
Voltage.
The contact of plate and
Oh, the contact in here? Yeah?
board and plate.
I think they're talking about from here
Yeah?
to here.
All right, okay, okay. Yes, but I think in the standard, they take the center. Yeah. Yes, yes, yeah.
The American code is following the edge.
Yeah, you just read it carefully. I need to check with the standard, and I think I'll check with Craig. He's the one who proposed this one.
Well, all we want to know is that which one is more appropriate. Because our code is not out yet.
Yep.
So we don't have a proper code as of today. So if we have to follow a practicing design engineer, should we follow the Australian code or the American code? Which one is more better?
That's a good question. I'm not sure which one is better. We need to have evidence on that. Yes, quite a little bit, right? Half of that one. So, as far as I remember, in Australian code we're using from here. Yeah, but American maybe you say that from here, huh? Okay. So let have a look later on. But just based on standard, what is written, you need to follow that. Okay. So if we're using the single shear width washer, and then with all the alpha is equal to 1, and you just plug into that equation, and you get the bearing capacity of the bolt connection. Right, so and then you use 0.6 is a load factor, a little bit higher than the other, and you time with, and then you get the total capacity of the connection because it has 3 bolts. You time with 3, and then you got total is 55. It's a lot bigger than the other failure mode, right? So that's what it is. Good. And then we check the tail. So the tail, T is a thickness, and E is 25. So in here you can see E is the center of the hole, not the bowl. And then the other argument is whether it's from the hole or from the bowl, because bowl is slightly smaller, it's shipped a little bit up, right? But I think in the standard now, they say that it's the center of the hole. So it's 25. Because you cut the hole right in the middle. Yeah. So 25. And you just plug into this equation, and you get what you want in here. 5 factor in this case, a little bit higher, 0.7. And you get those equation, and you got the capacity in town. 3 of them, so it's 44. It's bigger than 30.85. Okay. I mean, at the end of the day, you have a slightly different in here, but look at 0.7. You got 30% to cover all that that uncertainty or something. Then it's set, I'm sure, for design. It's pretty step. But then depend on the distance from here to here. It's all your definition. If you're using this one, it means that you have to calibrate based on what you choose. I'm not sure about American when they calibrate based on this one, so I need to check. Yeah, are you saying that in ISI? Oh, that's interesting. I will need to look at that. Maybe I talk to Ben Shepherd about what's that.
Professor Litte has done some cases.
Oh, he did a lot of block shears and bearing.
Water they use is slightly.
Yes, yeah.
Paper that came 3-4 years ago.
I know, yeah, yep. And then he did a lot of work on even this equation. He changed actually. I talk about that tomorrow, about what news. So what news tomorrow is we're not using this one. We replace by his equation. And his equation is slightly different. I'll explain to you a little bit. I'll jump ahead tomorrow, okay? So what happened at the moment we just consider the shear plan is at outer here, okay? But what he proposed is he using something, what he calls average shear plan. So he using something in here, right? So he put in the middle of this, in the middle of that, and then this is the plan that pull it down. So this one is not here, but somewhere in the middle. So that what he call is the average shear plans. So it's more accurate than, and then in right here, that's what we use in our standard in here, okay? We're gonna talk about that later tomorrow, how it works tomorrow. But for now, this one cover the standard. Are we gonna have break? We finish that example and we have break, okay? So you can read in here as the distance from the center of a standard hole to the end. Okay, this is clearly say in Australian standard is standard the center of the hole. Must be greater than 1.5 df, and df is the diameter of the bolt. Okay, so just clearly define in here for you. And this is meeting our requirement. So see the final solution is 3M12, 4.6 normal strength steel in the space 36 millimeter between the center of the hole, both hole, and 25 millimeter from the edge. And it's controlled by the plate strength design, okay? So all the calculation related to the bolt, they're all good. Bolt in shear, bolt in bearing, bolt in tail, the other limit state, they're all good. So at the end, the 30.85 control. So let's going back to 38.5, what is that? So that is this one, all right? Yep. Yep. Right. Interesting. Yep. I'm glad that there's a lot of very thorough question and detail on that one. I'm pleased. And now I learned about the edge from AISI. I didn't pay attention on that. Good to look at that, and then maybe I will ask Ben Sefer about that question. He knows exactly what's going on with the American code. Okay. Right, now, any question from this? All good. All right, we have a break. And we'll come back and do another interesting example as well. Right.
Take the number, the problem given three number of cases.
The problem?
State there are three.
Particularly for screw connection, we test a lot of them and we see a lot of variation. Normally we have to test 4 of them, exactly the same configuration, but we tested 4 and they all vary, maybe sometimes 20%. And then this all is not easy to understand. It's so depending on a lot of things. That's why when we calibrate that, the factor is low. And one more thing is, when everyone familiar with how we do the calibration, we have to base on beta. Beta is safety index. So for member, beta we use 2.5. But for connection, we have to use beta is 3.5. A little bit bigger, and then when we put our equation for calibration, it is dropping down our phi factor. Because the nature of the uncertainty of the connection, that may be effect of the safety of the structure. So that's why the calibration factor will be going down. It's good. Right, so now we're coming back to the next type of connection. I think interesting, because it's very popular, very common in cold form steel, that is screw connection. And here showing you different type of screw, from a big one to a smaller one with different diameter. And those one are tapping, self-tapping. So back into your question, do you see that? From here to here, they have a bit of that special tip, so it actually can cut the steel before they can screw it together. So you don't need to make a pre-drill hole, just use that and cut through the steel. All right, so in here, other than the diameter, you can see how coarse and fine of the thread here. It's very fine here, but it's a little bit coarse, and it's, you know, it's the so it all depends on what type of screw that you use. Right, so that number at the back here telling you how much is the fine or coarse. So you see it, number 24, it means the 24 of that one per inch or something. There's some definition on that. So the failure mode of screw is similar to bolt. You can see when it's under the tension, you pull it out and it actually cut the piece of steel out. Is similar to bolted connection. That's called the tail failure mode. And you can see that when it's dragging, there's a big air here that is causing the bearing of the hole. Same with the bolt connection. And this one, you can see, yep, if we use a very thin bolt screw, and it just cut through the screw. All right, so that is the screw in shear. But this is interesting. This is something new that you can't find in bolted connection. That's the tilting failure. Anyone heard about tilting? Yeah? Okay. So in steel, in cold form steel, if you put two thin sections with the screw where they have very similar thickness, and you can see what's going on. There's no bearing of the plate, but the screw just starts tilting when it gets to the maximum. They just keep tilting, and then it fails. Right, so that failure mode is called tilting failure. That's very popular in cold form steel. So it's tilting. So this is tilting when we test it in our lab. And this is part of the test that Professor Colin Rogers, when he did PhD at Sydney Uni a long time ago. So Professor Colin Rogers is one of the full professor in McGill University. Have you heard about that? In Canada, Montreal. So he's one of the experts in cold form hot rolled steel, and he's a Canadian. So he did PhD back into a long time ago, 30, 40 years ago. And all his tests on screw was used for calibration of the Australian standard equation for all the tiltings or bearings, so that all based on his work that we have. Just something to share you about what behind all that equation. So it's very good work from Professor Colin Raja. And this is bearing. Okay, so you can see what's different between that one and the one before. So this one of the tests we done. You can see now using exactly the same screw, but this plate is thicker. And you can see that one very thin. And what happened? That plate is just keeping going up. It's bearing a lot in here, but screw still really almost 90 degrees, so it's still there. So it's actually happening in the bearing capacity or bearing of the thin plate. So you can see, if you look at this one, you can see it's dragging in here. It's just bearing, and bearing. So that is another, it's similar to hot rolled steel, to bolted connection, where you see the bearing failure. So with geometry, the thickness T, T2 and T1, when you use the equation. So normally there's two plates, and there's the plate on the top, T1, T2, and so the dimension that you should pay attention on that. So again, this is all the equation from Australian Standard, and then is where we, Professor Hancock and Professor Roger Labu, Colin Raja, calibrate. So this is all the bearing capacity. You see that slightly different with bolted connection, depend on C and depend on a lot of T1, T2, and those ones. So C factor, you can look it up in the table in the standard, showing you depending on the thickness and ratio of different thickness, and then it will show you exactly the case that you need to work it out. And then depending on, you can see here, the ratio between two thickness. If the thickness 2 is a lot bigger than thickness 1, then and you have to use slightly different equation. So it's more complicated than the bearing equation that you use in bolted connection. So with screw on itself, there's a lot of equation. It's not it's not hard to use, but you have to be careful to choose the proper one, depending on what type of configuration that you use. Right, so this is equation from different situation, but somewhere in the between, in the middle, how you're going to do it? So you just use the interpolation. That's to work it out. Now, these are different as well. So we need to design for tension. So what I draw in here, you see that is part of the decking, a roof sheeting on top. So normally you have roof decking, isn't it? And you have the purlin down here. Okay? So you got to put the screw on here. Okay. So in some case where our structure or our building is subjected to wind uplift, so wind blow in, the lip is just blow up. So that screw is very important for design of screw in tension. And now there's some scenario that gonna happen. But anyway, in the practice, you might screw the bottom one, or this one, or you might screw on the top one here. Okay, and this all depends on how you're going to do it. But I think the top one here is good because it's going to avoid the leaking. Water is going to be here, maybe it's leaking in here. They put it on the top. It's better. That's what I think.
Prefer the crust fixing, sir? Screw
water leaking, maybe the low water on the top. But I think in the practice, normally they have the rubber washer somehow in here, right, to stop from leaking. So that's how it works in the roofing system. But sometimes they put on the top of the roof, not on the bottom roof like the other. Right, so in here, there's two equations for pull out. Pull out failure and pull over failure. It's a lot different, but now we give a definition. So with pull out failure, it means that if you have the screw here, and then this is the decking, okay? And if you pull it, it's got like this one, okay? So it means that there's nothing to do, nothing wrong in here. They just keep that screw and they just pull out in here. So that is when you use the first equation, all right? But if you put the screw strong enough into the bottom one, and then the top one is a little bit thin, it just pull out. So this one called pull over. So the head, it just went through, and then the fracture, it make that hole is torn out, right? It's just like this one. So this is the second failure mode that you have, which is the pull over. So we need to check both of them. You can see interesting here. Pull over depending on how big is the head or the washer. So back into your question you asked before. So DW here is taking into account the washer as well. So pull over really depends on the area that clamp into the decking, all right? And pull out, it's just depending on the hole, the screw only, the body, all right? So that's two different failure mode depending on different right, so with pan fasten is the one on the left, with crest fasten on the right, you have slightly, a little bit different equation depending on the one that you use. All right, and then in here, it defines on the detail on C, it depending on the corrugated or wide span or narrow pan, it all depends on the configuration of the decking that you use as well. Yes? It's just the calibration factor. But yeah, they based on testing. So they test a lot of them, they put a factor on that one. Okay. It's no meaning of that, it's just calibration factor. Yeah.
So the number of threads in contact with the second frequency tools will have an influence on the load variant. Number of threads, as you know,
Number of
threads.
number of screw? No, thread? No. Yeah, it's not included in here. Yes, so interesting on that one. But at the moment, in this equation, we don't have that to come into play. It's all about the dimension. So I think they presume that it's clamped somehow and pulled it up. And you have to pay attention a little bit here. The threaded of the screw is normally very small for the cell tapping. But with the cell drilling screw, we have a deeper thread. So we did a lot of tests recently because you remember the dimple holes that I showed you before? Because they have the pre-drill hole, then we have to use the the cell drilling. So the shape is a little bit different. They don't have the tip to cut. But the thread is a little bit deeper. I don't know why, but that is how it works in the practice. But for those type of screw that we use for testing in here, the diameter of inner and outer, including the thread, they're not much different. So that's why we can use that equation. Yes?
How we can classify this wide pan and narrow pan shooting?
That's a really good question. I think there's more information on that on the standard. We should look it up, and then there's some detail about why it's here and there. So it will show you. But it's in general, okay? But let's have a look at later on the standard. I'll show you.
So what is the below the specific
The K here. So K is a factor. I need to look up as well. Okay, some factor related to some variables. I look it up and see what is that in the standard. Yes.
crest depth, road area.
You mean the depth? The depth of the crest? I don't see anything that related to that the depth as well. It's just the configuration. If you use that, use this equation. If you put on the top of the reef, then you use that equation. Otherwise, quite complicated. Yeah, it all depends on how you design. So we need a more test on that. Now, that's it for screw, and now it's welded connection. So this very basic weld connection. Probably everyone know how to do it, right? So first is the butt weld, and this is Phillips weld, and this is what we call is the spot weld. Okay. So this is different because with thin wire, the top plate is very thin. So actually we can put the weld and melt it to the first plate, and it melts it down to the second plate. So you actually can do that. So this is what we call spot weld, and you instead of one dot you can drag it, and then you have a longer spot weld. And this is different. And flare bevel weld or something, because normally you welded the angle section into the other member, like a angle clip to the top flange of the girder, something like that, similar. So you can weld it in here. That's how it works.
What kind of welding? Manual or automatic? Any type of
It's up to you. I mean, when you do it in a practice, there's no rules in here by you using a machine or doing different type of welding. It's just it's a weld, and then the property of the weld, Fy or Fu. Yep. So that is depending on the welding technology, technique.
that will increase residual stresses.
So as far as I understand, in the standard, we don't say anything about what type of weld or weld technique that you use.
But what is the common practice in Australia?
It's variable. It's vary. It depends on the company. It depends on construction contractor or whatever they use. They can use hand or I have no statistics on that. I don't know, so I can't share with you because I know exactly what's going on. But I think it all depends. Yeah, it's not really 100%. Like in Australia, we do that way. It all depends. Okay. So with thin wall or cold form, normally you have single lap, and then this is popular as well. And sometimes if you want to make it concentric, you can bend it a little bit and weld like this one. Is it possible to do that? And you can weld it transversely or longitudinally. So that's different way to do it. Okay, so with the welding in cold form steel, I think I have a lot of questions on that because it's such a thin structure, a member. So when you put a lot of heat, then it might get some problem with the heated affecting zone. So what happened is when you weld it with the 3mm weld, it actually fell not right at the weld, but just the area close to that where the heated zone is affecting your structure. So you have to be very careful on that one. But it's just the technique, nothing to do with the design. Design, we just check when you already done it. So you can see here with the weld connection, there depending on the direction as well. So give you a different equation. So when you weld on transverse direction, you use different equation. In the longitudinal direction, you're using different equation. And then it's again about the ratio between LW and T as well. T is the thickness, LW is the length of the weld. So if the weld is long, relatively to the thickness, then you use this equation. But when it's smaller than 25, then you have to use a slightly different equation. So what does it mean is complicated, right? For the design, not just welding. You can see it back into the last couple of slides I show. It's just for even for pull out, for tension and for other stuff. Bearings, not just only one equation that you use as a whole. You have to, depending on a lot of factor that we use. Yes?
We have taken the belt strength FU as it is. Since it's a shear gradient, both in transverse and left direction, is it not 1 by root 3 times FU?
Now, FU here we use we just get from the property of the weld. FU is just the ultimate strength.
It's only 1 by root 3 times FU will be the shear limiting stress.
We don't, we consider as the ultimate. We're not consider it's in shear or in stress in here. The FU in here, right? Yep. So it's all like go to ultimate FU. Yep. FU.
Stress during transverse directional movement of two plates. Shear stress is induced at the point.
Okay. So I think in the connection is they make it simpler. They just use FU. FY, I understand what you mean. That is shear stress, right? And FY and FU is more complicated in this case.
Higher than what is?
Yeah, but in here they use ultimate. It's the highest one already. No, we don't need to. Yeah, we're using FU in here. Yeah. So FU in the just to make it simpler for the designer to use that. So once you have the weld, the classification of the weld, and you know FY and FU of the weld, and they just use that. So
Is inbuilt in the FU itself, or it's only material ultimate stress FUs?
it's a material property of the weld. Yeah, just simply how to do that. They calibrate by on that. Yeah, to make it simple. Yeah. But you can see FU is ultimate one. Of course, you get it from the test and then from a classification that you have. Right, and the other problem that you can see here, when you put a weld and you pull it down, there's a lot of curling problem. And you got here is buckle plate. So what happened in here, when you make the weld and you pull it, and this plate on that area is under bearing and compression, all right? But the nature of the thin wall in that area is very thin. Sometimes you remember it's 0.45, 0.42, the thinnest one, or generally 0.75. So it might buckle locally in that. So it's what we call is the buckle plate. It might happen. And that's what happened in here. So slightly different filer mode where you look at in terms of the behavior in the connection in cold form steel. So flare weld is just the way that you do it to connect, and then there's an equation for that as well in that cases. So now I'm going to show you an example of the weld connection. Okay. So this is the connection that connect the plate 80 millimeter to another one is wider, and we can use two type of weld. All right. First is we weld along the length, or along the direction of the loading. We call it longitudinal direction, and the other one you put in here, the transverse. We need to check, or we need to design. Okay, and see what's going on. So our connection will be subjected to the load 52.02, and then now we need to check. We decide how long we need to weld for the longitudinal welded in here, and on the transverse as well. So first is we look at the material property. So the plate here, we use normal strength plate. Then FYU is 300 megapascal. Sorry, FY is 300 megapascal. FU is the ultimate strength, is 340. is typical normal strength steel. And when now we need to check the tension capacity, okay, of the steel. So because that one is smaller, so we check for smaller one. So that is the width, 80. And the thickness is 2.5 millimeter thickness. So that's what you have the area, you time with the yield stress. And then you got 60 kilonewton. So that is NT for yield. Then this one, we check for fracture, but at this one, you know, we don't have the hole. Remember, with the bowl, you cut the hole, you need to minus that area. But this one, we don't have. So AN here is similar to AG, right? And then we check it. But with the fracture, remember, we use FU. But with that one, we use 0.85 in front. So then ultimately we calculate is 57.8. So with only the tension of the plate, we have two criteria to check. One is yielding and one is fracture. So fracture now is govern our design, a little bit smaller. So we pick the smaller one, and then we time with 5 factor 0.5, and this is the capacity of the plate in tension, the design one. So 52.02. Anyone good? Now from that one, yes.
Here actually we don't have any net section.
Yes. We don't have net section because we don't have the hole.
Do we need to consider the net section, that those ultimate fracture also?
We just have to check. Yeah, we're not sure. Yeah, it's separate to check both, even though it doesn't have the hole. Yeah. So now we look at the longitudinal welding here. So we assume that we have the case where LW is the length of the weld divided by T greater than 25. We assume that first. Then we calculate the equation here, the shear capacity of that weld, all right? So it's FUL times with thickness times with 0.75. And because of the welded 5 factor is 0.55, then we put in this equation, then we can back calculate the L. So the required length of the weld is 148 millimeter. Okay? And then because we have two legs, so one on top and one on bottom, and we divide it by 2. So each one you need 74. So and then we check again with that assumption that we made at the beginning. So it's 29, so it's good. So our assumption is good. And if it's no good, we have to do it again, the other way around. So it's good, our assumption is good. So then we calculate the transverse one. So the first one is we assume that we weld it all along here 80 millimeter width of the longitudinal, this is transverse weld. We put that one. So we calculate the VW for the transverse one, that one. So it's 80 is the length, and 340 is FU, and T is the thickness, is 68 kilonewton. We time with 5 factor. In this one, it's slightly bigger, 0.6. So what we do, we have ND, and then with longitudinal, with that one, and we got the take ND, we minus with the transfer one, and we got a 11 is the remaining load, capacity, right? Because we already, that guys, the transfer, we take the full length, and it will carry that much, and then the rest, the longitudinal will carry. That's how it works. So we try 15 first, And we plug into that equation, and then we calculate, and we got 7.917. And then because we have two of them, then we calculate that capacity, all right? And it's greater than the remaining load that we need, so it's good. So each side is 15 millimeter longitudinal well, okay. So with this one, how it works. First is we calculate the load that carry the tension load, and we assume that the transfer will carry all of them, and we minus this one, and then we got the rest. And the rest we just divide it by 2, and we assume that much, and we calculate, and it's bigger. And if you assume that, and then you get a lot bigger, then to optimize that, you just reduce until you get the one reasonable long enough, and then it's all good. So it's part of like a try and error procedure to make to go down here to get the optimum design solution in here. So that's for welded connection. Now perhaps in the standard, there are different type of the PAP as well, depending on companies and manufacturers and all type of that. So this table listed different PAPs that you need to use if you use that, and you can use it in the equation. So quickly give you different PAPs equation. They are different with the screw equation. Right? We thought that they're going to be similar, but they are not. As I mentioned, there's a lot of things happening in the plate, and it's not like screw. So that's why the equation here is very imperial equation. It's all based on testing. They're calibrated based on the test data. So it's shear strength, bearing tilting, and pull out. The whole equation is in the latest equation for AS and ZS 4600. It's a brand new one. I'm gonna spend a lot of time for tomorrow lectures, and we can decide that. Yes?
In that equation, if y is the lowest one, if y2 or fy square.
F is this one.
Yeah.
This is Fy is yield stress of the plate because it's full out. The plate, the base plate.
So is it the square of the fy?
No, Fy2 is the number 2. It's direct. It's not, yeah. So number 2 is the plate number 2 is that. All right. So I will go to those equation because it's new. So I will cover in tomorrow lectures about what new. And this one is new. It's not in 4620 2005. So what's going on at Sydney Uni? We did a lot of tests to see what's going on with the screw connection and with the PAP connection. You can see this is PAP where we test in the single lab, and here you can see a lot of filament that we see here, bearing the formation of the PAPs. Very complicated. But we're getting there. We're gonna have a lot of interesting results that we might share with you later on. So even with PAP as well, just on this, explain to you a little bit of behavior. So there's some filament very interesting because the bottom is thick and the PAP is going this way, and you pull it down, and if this PAP is strong enough, and it just tilt a little bit and just pull out. It's pulling now. So that filament we call is pull out by shear. It's not pull out by tension. You mean that in this way you pull it up, so it means that pull out in tension. But then the other way around, if you put in shear, you still get a pull out, but it's in different filament, in different action. So very interesting. That one you can see only in the PAPs only. So we're working on that. We come up with some proposal in the standard later on. So for the connection, you can see is, we're testing. This is the beam. This is connection. We're using 2 PAPs connect the cold form steel. With the yellow one is the hollow angle, hollow plate. So we're using here. This hollow is 10 millimeter thickness. So we packed our 200 millimeter depth of cold form purlins into that. You can see there's a lot of deformation or bearing in here. And interesting here because this is the connection at, for example, the building connection. And the connection here is a little bit more complicated. Right. So remember when you do it now, when you design connection, for example, to shear or screw connection, what you do now, you just check shear or bearing or whatever in one screw. And you time with the number of screw that you design. That's it. That's the capacity. So in the practice, what you do, for those type of connection, in the practice at the moment, if you have a beam, and if you have to tap in here somehow 2 screw, you tie with the, this is the column maybe, 2 screw in here. Right. So what you work it out is you calculate the load acting on the beam or whatever, and at the end you calculate the shear load in the support. And now the shear load, and you back calculate as we just designed, right? And then you back calculate the shear capacity of one screw and 2 screw and bearing or whatever, and then you take this load divided by that, you know how many screws you want. Okay, that's how you work in that. But in the practice, the screw here not just subjected to one single action. Yeah, so you can see here because a lot of rotation and a lot of shear in here, so it might reduce the capacity. We don't know. So we need to come up with the design model for that type of connection using our screw or pipe connection. So that's where we come up with the very complicated, not very complicated, what we call is dual actual test strip. So we are probably the first one in the world build up rigs. So we have 2 actuators, and that actuator, 2 of them are just on this share when you are on in terms of research, okay? Nothing with design. Design is very simple what we are, but in terms of research, what we do here, so this is we're trying to test the connection. So what happened is we have 2 actuators to bring it down in here. So that actuator actually creates the shear load, as you can imagine in the practice. But this actuator pushing down, then we can control the rotation. Because the beam in the practice, right? The beam and the connection, it is not just subjected to shear, it's subjected to the bending, and when it bends, it rotates. Okay, so that combined rotation and the shear might reduce the connection capacity in the combined action. We don't know how it works. And the complicated function of this test rig is they control this one, actually, what I'm saying, they talk together. So this guy going down and read the shear load and then fit back to this guy. And this guy will run up and down, even up or something. They make sure that we target one ultimate load or whatever we want to target. So very complicated test setup, but we can get what we want. So the ratio between the rotation and shear and the one that we design for that. So a very interesting test rig. If you're very interested in that, I will send you our paper and our thesis that you can have a look, and then you can find some hopefully useful information. So that is what we tested at our lab now at the University of Sydney, and let's just give you an update about what's going on. Yes?
Those are through the CG or through the top match?
This one. So what we do, you can see we transfer the load from here to the thicker plate, and the thicker plate we transfer to the big bar in here, and that bar we push screw.
The CG only you're applying, CG of the section.
Yes, CF section, but we just transfer the load to the center of the web. Yeah, we don't push on the top in here. Okay. All right, so that is what we call is dual test rig that we come up, we design. And just recently, we got one PhD student, he just finished. We got another actuator on here to control the compression as well. So even more complicated, we got 3 actuators talking together, how it works. So it's really simulate the real situation. Then by doing that, we hope that we can understand the real behavior of the structure of the connection. Okay. So in summary, we just highlight about what's going on with the connection in cold form steel. So both the connection have a greater propensity in bearing, and that require a washer. So both connection a little bit different. With screw connection, now screw is something new, so it can tilt. So what we learn, as well as bearing. If you use very thin section, there is bare, but sometimes if you use 2 of them with very similar thickness, then it might fail in bearing, in tilting. And welded, as we always warning, as some problem with heat affected zone, we have to be very careful, and then that's why we need special rules for that, to make sure that we cover that. And in cold form steel, we're using the steel grade is high strength steel for G450, and something new is power actuator fastener, how to design that. So tomorrow we will cover that, give some example on that. With that, I finished the lectures on connection, and now any question? Happy to take. Yes?
All the designs that we have done is for a particular member and section, right? So when you said you have designed a new storage unit with core function, so what software do you use for the analysis?
Software for analyzing.
It's when you go and the column and transfer the.
Okay, so in structural analysis, right, you're normally using your whatever the package that you use, and then the thing is you need to assume that the connection between the column and the beam is a hint, right? Because with screw connection, with 2 bolts, it's not going to carry the hooking moment, isn't it? So what I mean here, you run analysis with a frame or something, but this one is a pin. So simply support it, and you can work it out easily, and you can calculate the shear force in here by a very simple equation. And from that, you can divide it by number of screw that you want, and you check with the 1 screw capacity.
I'm talking regarding jet, like both of steel has very unique sections. Like Super C is there, Super Jet is there.
Superjet, yeah?
Not most of the commercially available softwares has those sections available for full form design.
Yep.
Like when we do in analysis, say we use CAD.
Okay, so you mean,
Is there any specific software for which we will use for analysis purposes for a whole structure or say a truss section?
okay, so you talk about 2 types of software. One is structural analysis. It's based on finite element or whatever, right? And one is thin wall, something that is buckling or the member analysis.
For the individual member, I'm talking about the structure as a whole.
Okay, you talk about that. So you talk about structural analysis software. So, for example, in US, you're using ETAP or SHAP. In Australia, you can use MicroStrand, or you can Strand 7. So that all the software that you use, you can run.
These sections are available there.
Good question. In Australia, software, microstrain, I believe that you can use that. You can choose in the library. It's somewhere in that one you can use that. Because it's all based on Australian market and Australian products. So all the section that built in the library is actually the one that Australian company produced that. All right. So I'm not sure about SAP. I'm not familiar with that for American one, but I'm sure that microstrain and Strand 7 because I use that for teaching. So I know that there's all the profile that you can find is all available in the market in Australia. Yep.
Typically, in hot steel, we classify the connections rigid, semi-rigid, and flexible.
Yep.
Radar Howden has done the work in the 70s.
Yeah, yep.
So,
Radar, yeah.
So we have adopted that in the Indian code. In the appendix, we have classified as based on the rotational capacity and the connections as rigid, semi-rigid, and flexible.
Yep.
And based on which we can detail the connection.
Yes.
So what is for rigidities and what is for flexible and semi-rigid. Do we have such classifications when we run the analysis for deep column connection in cold form steel to classify them as rigid, semi-rigid, and flexible?
As far as I understand from Australian code for cold form steel, the answer is no, we don't have yet. Okay, and that's why the previous one showing you our purpose. Okay, the last okay, so the last slide. Here we start to get to the problem a little bit more complicated where we consider connection subjected to rotation and shear, and then we come up with some model to design for that one. But at the moment, everything that you do, everything is in standard. You treat the connection is the multiple of a single screw or bolt or whatever, and you just multiple with the number of that. That's it. So you work it out the shear, and then you divide it by the number of screw or number of bolt, and you design for that. There's no definition about the the simply supported or fixed end or semi-rigid or whatever in the connection. But we test a lot of connection. It's very hard to get to the fixed end. We tested already with the cold form steel, and as long as you make it very, very steep, so you got a big plate on the top, big plate on the bottom, and you have to screw a lot of screw on the top flange and the bottom flange to carry the hooking moment. Otherwise, if you just bolt it on the web only, as in the normal practice, you're not going to have a lot of the bending that can carry the hooking moment. So to simplify that, for cold form steel connection, as I understand now, they will assume that is hinge connection.
So our research also indicates the same. Even if you put the number of screws at the flanges, if we are not able to achieve it.
No way, yes.
The maximum we can do is semi-rigid. Maybe one or two specimens actually slightly exceed semi-rigid,
Yep.
but 90% of the specimens we test actually fall in the semi-rigid category.
Yep.
So they are better than flexible, but certainly not.
Now, yeah, so cold form is pretty tough, to get to that one. Yep. But the combine we can in here. The combine between rotation and shear, then we need to take into account. Yep. Even though in general, for structural analysis, when you run it, you assume that it's hinge. But when in the practice, of course, you got two bolts, you get a bit of rotation, of course, you got a bit of resistance. So it's not 100% pin, but then you need to design for that. But for structural analysis of the whole frame or the system, then you assume that it's the pin end.
I have another question. So you wrote about the anchors at the bottom, right? So you have a hot rope anchor, and then you plug it into the base of the concrete, and you were talking about the filtered length. So if it is for a foundation, I think I can go up to say 150 mm.
For foundation,
Yeah,
yeah.
but if you're putting on top of a flooring system, would you like to have 2 to 2 threaded rod?
That's really a good question. I need to talk to the company or who done it. So I'm not 100% sure how it works on that one in that application where they make it and how they design it.
The reason I ask is that at least I come across projects where there is a need to put one floor above, especially people in Delhi like to have one floor above, which is light, and then you don't have to change the foundation. But the biggest problem there is that it has been properly anchored.
Yep, anchor.
You are anchoring on top of an existing flooring system.
Oh, yeah.
And many times the threaded rod length actually exceeds the thickness of the floor. So
Yeah.
for the ground floor it will look odd that the threaded rod is getting exposed, right? But sometimes we feel that even that is not sufficient in case of there is a wind or overcoming.
Yep.
So do you have any thoughts on that?
I think it's very special situation that we are engineer. We need to deal with that. But in general, in the standard, we don't have any problem where we just check single poles and that. But I get your point. It's complicated if you go in that different complicated scenario. I think in that one you need to treat as single cases. You have to deal with that, design for that.
So one of the contractors was regarding what you just said. So what they did was in the slab, and with that they tied the RF. So the RF was 75 mm. So it's more like this on top of slab they were tied to achieve the anchor that you're talking about. And then there is 100 length, that's the anchor 100 length. They put in that anchor here angry, and half of it they insert. So they say that that is how we achieve that landing. What is the RF was minimal, 10 at the rate 270 push another like this year. On top of the slab, they put the heat anchor both the distances.
What is the RF? What is the one country who is in
Yeah.
sheer real?
That is what we told them. That's why the heat.
Some very interesting problem. It's not covered in standards. So they ask the question, what are we going to do now? Unfortunately, you have to convince yourself how you're going to, because it's not covered in standard. We don't know. And then what in standard? It means that it's already validated or based on the tested and all calibrated by, we all understand how it works. But sometimes, some way, and then something new that it's not covered, and then we have to convince ourselves to do it. So great, yeah. Any more questions?
So if there are any more questions, we have an announcement. Professor How Kong will be giving a research talk today at 3 o'clock. So